TLA idea of educational items for the AV Lab 2. And Group 3, you guys ready to explain precisely what you guys did on the last 2 semesters?
Yes, sir. Yes.
Go ahead.
Good morning, everyone. My name is Brian Benoit. This is Morgan Ewing, Maya Garza, Claudia Gomez, and Eddie Perez. And we are the TLA Heating Group, and our project is the design of an automated heating system to supply educational heat exchangers. The purpose of our project was to design, fabricate, and test an automated water heating system for laboratory-scale heat exchangers to ultimately replace the DLMX units currently in use in the UT TLA lab. Our project differentiates itself from the current lab setup by offering automated temperature and flow rate control, the ability to deliver greater volumes of fluid, which will allow for potential future expansion to multiple heat exchangers, and accuracy. Now Morgan will discuss marketing considerations.
Thank you, Brian. So what makes the TLA heating system so great is not only is it intended for educational purposes, but it also has a unique design. And what I mean by that is you're not going to find anything on the market today that's quite like it. If we were to compare the DLMX system with the TLA heating system, we would be able to show significant advantages with our system, with control of temperature, flow, and pressure, 2 of which those controls are automated through the use of LabVIEW software. This will allow universities to kind of supply industrial applications and controls, automation, and data acquisition and bring that straight to the classroom. Another great advantage of having the TLA heating system is that there is no direct encounter to hot fluid whatsoever, as our system is completely enclosed. As you saw before with the hot plates and the hot water pitchers, if a student has to carry that hot water pitcher over to the DLMX and pour hot water into that open tank, then they are potentially at risk of becoming exposed to that hot water. This is a huge disadvantage of the DLMX and also a great advantage of having the TLA heating system. Now I'd like to briefly discuss with you the design considerations. The University of Texas at Tyler did request that we follow operating conditions such as temperature range and flow rate, that temperature range being between 70 degrees and 140 degrees Fahrenheit, and the flow rate between 1 and 15 liters per minute. Additionally, we did have to take into account that the majority of these experiments would most likely be performed in a laboratory environment. With that being said, we were able to assume that the most convenient and user-friendly power supply would most likely be an electric power source. Now, with each electrical component, we did have to consider environmental regulations as well as electrical code and ethics. All of those are present in our operations manual. We do have a copy of it, so if you would like to refer to that after our presentation, please feel free to do so. With these design considerations in mind, we were able to come up with a conceptual design. This is basically a mapping of all of our preliminary components that we thought were necessary for our initial prototype. So starting with the reservoir, we knew that we would need at least a 4-gallon tank to provide flow to multiple heat exchangers, as well as a recirculating pump and electric heating element. Now once that flow goes through the heat exchanger, we knew that we would need some means of a chilling mechanism to be able to send that flow back to the reservoir without disturbing the temperature inside the tank too dramatically. From the conceptual design, we were able to add additional components to improve our efficiency and accuracy, such as sensors, our automated controls, and the addition of a mixing chamber. And now I'll pass the floor on to Octavio, who's going to go over the final design.
Thank you. Our final design is composed of a pump that provides the flow for the system, 3 actuator valves that are in charge of deviating the flow to the heater and chiller, depending on the situation and what temperature we want to reach. We have the mixing chamber that provides enough space for the hot and cold fluid to mix in order to obtain a stable temperature that is going to be controlled. We have safety features as 3 check valves to prevent backflow, 2 bulb valves to avoid any leakage when we are disconnecting the system, and a pressure relief valve in order that just in case if the pressure builds up, we can release all the pressure without damaging the system. When the system is working, 2 main types of flow is going to occur. One is going through the heat exchanger, is when the system is operation in the lab setting. When we want to reach a certain temperature quicker, we the flow toward the heat exchanger, and we recirculate the flow in order to be able to control better the temperature. When we want to cool down the fluid, one actuator is going to deviate the fluid towards the chiller. This allows to decrease the temperature quicker before going to the mixing chamber. In a similar way, when we want to increase the temperature, another actuator is going to deviate the flow to the heater before going to the mixing chamber. Now I'm going to pass on to Ed to explain the electrical components.
Thank you. So, as you can see, there's a lot of electrical components in our system that take into play. So, essentially, this is our control layout for our power on our electrical components. And what we have is a main breaker box with two breakers, a 20 amp and a 15 amp breaker that feed off 120 volts. Now, the 20 amp breaker actually powers both the heater and the chiller, whereas a 15 amp breaker actually powers all the other auxiliary systems. So some of these auxiliary systems include a 24 volt AC transformer that powers our three actuators, as well as we have an AC to DC converter used for the flow meter, and we also have pretty much a pump that's powered on by those 120 volts. So this next portion shows our control panel, and the way we have set this up is that we have 4 toggle switches. One toggle switch per each actuator, as well as one toggle switch to actually give power to the whole system. So as you can see here, we have an indicator light for each one. When we toggle it up, it is actually in manual mode in case you want to do any testing of the system. And then we can toggle them down whenever we want to have control through LabVIEW. And we also went ahead and included 4 fuses for our LabVIEW inputs, and that's just to protect our data acquisition module, as these use low current for any shorts or any high currents. So essentially what the user is going to do is whenever they look at our LabVIEW software, this is the interface they're going to see. So it's very similar to what we have on our control panel, where we have one toggle switch for each actuator, but we also have an additional toggle switch that will give them manual or auto mode from here. Now, whenever the user sets it to automatic mode, what's going to happen is they'll go ahead and power on our system, and it will let them know once the system is ready, and they can go ahead and input the target temperature. Now, our system will go ahead, and depending on what temperature they put, it will output the corresponding signal to the actuator, whether we want to heat or chill, and reach that desired temperature. Now, an additional feature that we included is that flow meter itself will detect if there is no flow. So in any instance like this, there could be a leak. And so we have a no-flow alarm that will go ahead and send a signal to a solid-state relay that powers the breaker box to make sure we can cut off all power and have no further leakage. So this is pretty much a general overview of how that works. The user will go ahead and set that temperature. Our LabVIEW program will sense whether we need an increase or decrease and send the corresponding output using a PID controller to reach the desired temperature. Now, if we don't detect any flow, then that will go ahead and send an emergency cutoff signal to the solid-state relay. So in total, we have 2 inputs, one for the thermocouple reading the temperature, one for the flow meter, and 4 outputs, one for each actuator, as well as one for the solid-state relay. And I'll go ahead and hand it over to Brian, who's going to speak about some of the calculations for our project.
So as our system is pressurized, we had to perform several calculations to ensure its integrity. We verified these calculations through simulation and experimentally as well, which we'll see in the following slide. These are some examples of stress calculations that we conducted on our mixing chamber. We have longitudinal stress over here, longitudinal stress as parallel to the long axis of the cylinder, and hoop stress over there, which is like a steel hoop around a wooden barrel. As you can see from the formula derivations, hoop stress is what is going to be greater. Now this table shows a summary of our results. As you can see, we cut it off at 60 psi because this was the maximum pressure that we could achieve from the city water line. An internal pressure of 60 psi leads to a hoop stress of 360 psi, and the yield strength of PVC is around 6,700 psi, so we operate with a significant safety factor. Now, Amalia will discuss some of the experimental testing procedures.
To ensure that our system can run efficiently, we conducted a series of non-destructive tests. Our system is specified to run at 30 psi. We tested our system at the maximum. Our system was able to withstand up to 60 psi with no water leaks. Next, we tested our controls panel toggle switches. As we toggle our switches upward in the manual override position, we could visually see as our actuators engage from resting position to operating position. Next, we toggle our switches downward to LabVIEW mode. From LabVIEW, we are able to access each actuator as desired. Now I'll hand this back to Brian, and he will speak about the test results.
Now, most importantly, we also tested our system for its heating and cooling capabilities. During heating, we were able to obtain a 60-degree Fahrenheit increase in less than 2.5 minutes. And during cooling, we were able to have a 34-degree Fahrenheit drop in the first 1.75 minutes, and then to return to room temperature, it did take another 26 minutes. This is due to the relatively small capacity of our chiller's tank. However, this is not the primary purpose of our project, and we were not overly concerned with these results.
So this next chart pretty much shows our testing results when we went into automated mode. So we can see the increase in temperature, and this is again in about 2.5 minutes. But we actually tested it from room temperature all the way to our max temperature of 140 degrees Fahrenheit. So what happens is that when we reach that temperature, our system will either kick into recirculation mode or send it output to the heat exchanger. Now, we did have a slight overshoot of about 1.4 degrees Fahrenheit, but the recovery time of this was about 35 seconds. And then after that, once we're either sending to the heat exchanger or recirculating, we have a temperature drop of about less than a degree per minute. So what happens is that we set our software for a 5-degree threshold. So whenever we drop below those 5 degrees, our system kicks back into reheating to get us back to that desired temperature. And I'll go ahead and hand it back to Brian, and he's going to speak about additional design considerations.
So another desirable design feature that we implemented in our system was a modular design. Our system consists of 8 sub-assemblies, which allow for preventive maintenance if necessary, ease of assembly, as well as the interchangeability of parts. Now, one of the most critical sub-assemblies in our system is the mixing tank. The mixing tank consists of 13 components which serve the purpose of bringing the hot and cold fluid together to form a homogeneous mixture. Now, some things we took note of was that the mixing tank had to be 10 times the length. The length had to be 10 times the diameter as a standard for mixing. Furthermore, small pipes flowing into large pipes often can create fluid segregation. To prevent this problem, we installed a stainless steel baffle inside the mixing tank to prevent this issue.
As Brian mentioned, all the assemblies can be found in our manuals. All of our tests, hand calculations, simulations were all consistent. Therefore, we were able to publish our operation and parts manual. Our operations manual consists of the priming and operating instructions, as well as our safety precautions. Our parts manual consists of the main flow, the main components, and all the individual assemblies that make up the mixing tank. Now I'll hand this off to Octavio, and he will speak about economic feasibility.
After taking in consideration the design and development time, we estimate the cost of the prototype is going to be around $90,000. We did a calculation for the mass production price of 1,000 units, and it's around $7,100. But since the scope of this project is limited, we decided to do a smaller analysis for 50 units mass production, and we estimate that every unit is going to cost around $2,400. In conclusion, our project was successfully achieved all the specifications that were required at the beginning of the design, but those are some improvements that can be done in the future. This concludes our presentation. We would like to open the room for any further questions.
Before I ask the question, I want to say something. This group has done a very effective job in demonstrating using the slides. Very good. Thank you. I actually can look at your slides and understand even if you don't talk. Some font was small, but we're good. We can do it. But the motion effectively, not disturbing, slowly was good. The cost analysis. Can you estimate? You can pull that up again.
Yes.
I think you said something that I missed, so I'm just asking for clarification. I can't read what's in the blue, but I think the first column heading is prototype.
Yeah, prototype.
Okay. When you say $10,000 for design, is that labor
design and development are the hours that were spent on developing the project.
Okay. But material-wise, it looks like the cost is $2,400 for the prototype. If I take away the hours, roughly,
Yeah. No.
or even $2,000. Now, what is the heading of the second column?
50 units mass production project.
So if you want to make 50 at mass, did you make 50 or did you estimate 50?
No, we estimate the cost if we want to mass produce 50 units.
Okay, and the third one, if it's again, it's an estimation.
Yeah, it's an estimation for 1,000 units.
Okay. Just how does that compare to the price of the system that people buy now and put in their labs?
The systems that are available, commercially available right now, are far more expensive, around the order of $10,000. When our system is complex, due to the capacity that is required for the scope of the project, since this project is designed to provide multiple heat exchangers that require big equipment, and those equipment tend to be costly.
And roughly, if I am not an engineer and I want to buy a heater for my house or whatever, how many of those do I need to heat, let's say, 1,000 square feet? A floor in a small house.
I'm gonna need more, but since the purpose of this project is not to feed a whole floor, it wasn't designed with a high capacity. It can be made with a high capacity by expanding using a regular heater and a bigger chiller unit. That will be the only modification.
Well, let me turn the question around. How much space can this heat in an efficient way compared to a system that's sitting there at some home or this building?
So this
It's the
system,
same question.
well, this system pretty much, what we have is set up for, I think our total circuit is about half a gallon of fluid, whereas a home you might have tens of gallons in the lines. So we have a 4-gallon heating tank, which heats up that water in our system effectively, and for the small heat exchanger, it should be able to do so with no problem. But as for a house, you're probably looking at more than 10 of these just to get the same job that a water heating tank can do on its own.
Well, I think it would just depend on the size of your reservoir more than anything. The purpose of our system is just to maintain a desired temperature. So depending on the size of that reservoir, we can supply water to a variety of different sizes.
Don't sweat it. I'm mixing two things and throwing me off. I'm mixing heating the air and heating the water together in the same question. So you should be able to split them, but that's just to throw you off. You're doing good. Thank you.
Okay.
Any other question?
Yes. How do you notify the user of an alarm condition?
I'm sorry, what was that?
How do you notify the user of an alarm condition?
So essentially, the clicker. What we have on the LabVIEW software, the interface has a no-flow alarm indicator. So at the bottom left, you see no-flow alarm. That indicator will essentially turn on and then just pretty much kill power to the whole system. So there is a solid-state relay inside that control panel, and that solid-state relay feeds all our breakers and everything, so we can cut power to the whole system.
Was there?
On that topic, what's the logic behind the no-flow alarm?
So essentially, if the solid-state relay is normally, it needs a voltage to stay on. So what we have is whenever we plug our system in, there's actually constant power to the AC to DC converter. And that is always feeding that solid-state relay when we turn the switch on. So whenever the actual flow meter detects no flow, so that's why I said there's a startup procedure. Our system will turn on and then wait until there's flow detected.
When I say the logic behind it, I don't mean the reasoning behind it. I mean how you determine no flow.
From the flow.
Oh, the flow meter. The flow meter gives out a current. So if the current is high, then there is voltage.
Right. But do you do any averaging, any time condition for no voltage, or if it just had an intermittent loss of signal, is it going to shut your system down?
So it is as soon as there's a loss of signal, is the way it's currently set up.
Yeah. Is there a way to be more demonstrative on an alarm condition other than that? Just come up, can I have a song or a horn or something like that?
That could be added onto the control panel. I guess that would be ideal, is to add some kind of sound so the user knows So that would be for future considerations as well.
So on that, the block diagram would be useful here because that's kind of where these questions are stemming from. I have a software question. Why would you choose LabVIEW instead of going with MATLAB Simulink?
So this is just a requirement given to us by the University of Texas. They wanted us to go ahead and use the LabVIEW software as those devices are more easily available for us.
But it wasn't listed in your requirements at the beginning.
Right, so that's just one thing that we didn't state there, but that's the reasoning behind it.
Okay.
Any other questions?
Yeah, quickly, I'm not complaining that there's a chiller in there. I'm curious why you put one in there.
So our heater reaches maximum temperature, while the chiller is going to flow into our mixing tank to reach a desired
So you
condition.
can't control the temperature of your reservoir.
Right, right.
You control outflow temperature by mixing ice.
Right, right.
And if I may, just one, I can't, your charts aren't numbered, so I can't get back to the chart I was talking about, or that I wanted to reference. You have a temperature range versus flow rate curve, or data at least. I was curious at those extremes of your temperature range, that is, say your hottest temperature, if you can actually achieve that at your highest flow rate.
So this test was actually done using our highest flow rate, in that we were able to achieve about 7 liters per minute for the highest temperature available.
Well, through what though? Through the heat exchanger?
So we actually measured that at the flow meter output, which is right before the heat exchanger output. So I think once we have the heat exchanger connected, those flow rates could vary.
But wouldn't that change with your inlet temperature on your circulation, which you're bringing back to your system? I feed you ice water. You're not going to be able to supply.
The thing is, when the temperature is not the desired temperature, it's not feeding the heat exchanger. It's recirculating until it reaches that temperature. Then it'll deliver at that max flow rate to the heat exchanger. So it's constantly recirculating.
So you have like a recovery mode where you're not going to be supplying
yeah.
the heat.
I think Octavio talks about it in his slide.
So you're not able to deliver continuous. So you might need to do
So like,
sort of-
if somebody requested 75-degree Fahrenheit water, we could deliver that immediately. And then if somebody requested 140, it would take 2.5 minutes to deliver that. Then if somebody asked for a 75 again immediately after that, that would take some time. But if you asked for like 130, we could chill it down in like another 2 minutes again. But if you want,
if I want 100-degree water and I'm feeding you ice water, you can only give me so much, and I'm not sure how much that is. Right?
this will give you 140. It will take it up to 140 because the max temperature in the heater is 140. So we'll recirculate it until it reaches that max temperature, and then send delivery.
Yeah, you're not producing any output at that point.
No, during that
so you
time.
have a low flow rate.
Right.
So yeah, we have a disconnect on your stack.
Yeah,
I just
during
need to understand that better.
during the time of recirculation, there is no flow rate to the heat exchanger.
Yeah.
The heat exchanger flow rate only starts when the desired temperature is
So
reached.
that's really your performance parameter. That's your ultimate performance parameter, right? Because you'll have people sitting in a lab station saying, "Where's the water?" It's not here. So you're waiting on it. Now that's okay if I can wait 2 minutes. It's okay. But if I have to wait half an hour, we have to go home.
So real quick, you don't feed this system any water, right? So like there's a system priming instructions where you fill up the system initially, and then we kind of instruct you maybe every 2 weeks to maybe refill it if to test it to make sure that it's full, right? And so the temperature inside the system is always at room temperature. So if we're going from room temperature to hot, it takes only 2.5 minutes.
Not if we're returning really cold water.
Oh, if we're returning from the heat exchanger. Okay, well, yes, but we kind of are. Okay, yeah, that's fine. But the thing is, the heat exchanger, that depends on the capability of the heat exchanger to reduce the temperature of the hot water. So if they have an awesome heat exchanger, yes.
Right. But
Yeah.
like for you, that's a mystery, right? That thing's a mystery. You don't know what it is.
Yeah.
We can have some magic.
Yeah.
Right, but we have enough fluid inside of our heating tank to allow continuous flow at a desired temperature rate continuously. flow back into the heater. And from the heater, which already has hot water, that's going to flow into our mixing chamber. So you do have that continuous flow, and the flow is controlled by our actuating devices.
So, yeah, do you have confidence in some of those numbers that you can support on a continuous basis?
Well, we do have the recirculating data, which, no, we didn't compare it to a change, a fluctuation in temperature.
Presentation, we can talk about it.
Right.
I'm kind of curious what the system is capable of.
Right, we wanted to test it with the heat exchanger groups, we just never had the opportunity to get everyone together.
But great job.
Thank you.
Do you have an idea of the overall power requirements of your system?
Electrically, we designed the system so there's a 20 and 15 amp breaker. I want to say in total we have about 30 watts. Actually, the heater itself will take up to about 100 watts. But I know the breakers were much overrated for what the actual use was, and that was something that was taken into consideration. Is that there were calculations done to make sure that we are within the current ratings for each of the desired components.